Okay, so welcome to Math 331, the little questions. This is one of my absolute favorite classes to teach. There are several reasons for that. One of the things that's really nice about this is there is no class that builds on this. We do actually have a class in the curriculum called the Big Questions. It is not a sequel to this. The purpose of this class is to just talk a little bit about problem solving. The goal of a professor is not to create more professors. The goal is not to clone ourselves. The goal is to give you the tool sets you need to do whatever you want in life. And so there is no set curriculum. There are no things we have to do in a class like this. There are almost surely certain things we will do, but there's a lot of freedom based on what you're interested in. The big goal I want you to get out of this is the comfort in speaking, the comfort in thinking on the spot, and the ability of looking at multiple ways of viewing a problem. Sometimes one way is more valuable than another. One of my favorite quotes, and people who have had a class with me know I say this all the time, is if all you have is a hammer, pretty soon every problem looks like a nail. What's going to be happening in this country in November? The election. And there will be at least one debate between the two candidates. I will risk saying this with the cameras rolling. It doesn't really matter what question you ask. Each candidate has certain points that they want to talk about, and they will find a way to, whatever you ask them, get into the pre-planned things that they want to say. They have their hammer that they're going to get to. If you're really good at something, if it's something you want to emphasize, if there's a technique you're strong at, whatever I give you, you try to find a way to convert that to a problem where you can use your hammer. So that's one way to view the quote. A better way of viewing the quote is if you are looking at the same problems as people with the same training, good luck distinguishing yourself, good luck being very successful. Nothing against you, but in elementary number theory, I'm going to go with Gauss over you. I'll go with Gauss over myself, right? If you're going against the experts one-on-one, it's hard to be better. If, however, you go to the land of the screwdriver, if they could have solved the problem with the screwdriver, they would have. They're not dumb people. If you have a different set of tools, you have the opportunity, okay, you've already tried your tools, let me try mine. I've written papers in accounting, in computer science, in economics, in marketing, in geophysics, in physics, in sabermetrics, so many different fields. And I've been able to apply number theory and combinatorics and items like this in very strange settings. And it's been very productive because I have a different way of viewing the problems. And that's one of the things I want you to get out of a class like this, is learning certain techniques which are almost surely going to be useful in different places. Another thing is I call this the baby crying method of mathematics. You want to have a bunch of tools and you just try them. If a baby is crying, what can you do? I will risk saying this out loud. What can you do if a baby is crying? Hopefully some of you will be parents someday, so this will be potentially useful.
Call the mother.
Call the mother. That's one possibility. So you can shake it a little bit. That's not necessarily the first thing you should be doing. What else could you do if the baby's crying? Close to shaking.
Change the diaper.
Change the diaper. Yeah, I missed that one when I was younger. So changing the diaper. What else?
Could feed it.
Could feed it. What else? Give him a bottle. What else?
Swaddle it.
Swaddle it. There's lots of things you can try. Why don't you just ask the baby why you're crying? It can't answer that, right? Eventually, after a while, you start to learn that's the I'm hungry cry. That's the I want to be held cry. And you know by hearing it which one to try first. And you have a better sense of how to attack problems. When I defended my PhD thesis, there were only two non-mathematicians in the audience. One was Dean of Student Life, because I was very active in that as a graduate student, and the other was my wife. And afterwards, she came up to me and says, "Oh, that's your I'm nervous voice." I'm sorry. That's the voice you used when you asked me out all those years ago. I haven't heard that voice since. But after a while, you start to recognize. That's one of the things I want you to do as you're looking at problems in this class. Start to get to the point where you can recognize, what should I try first? Eventually, AI is going to completely come in and revolutionize things, and it's not going to be so important because AI is just going to try everything in extremely rapid succession. Boom, 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 boom. They're talking about in a decade, you will have millions of copies of AI at the level of graduate students able to attack problems. And it's going to be really interesting to think, how do we have to adapt? And again, this is something I'm absolutely happy to talk about in a class like this. What is your career going to look like in the coming AI era? And a lot of it is, can you be creative? Can you deploy stuff like this well? And so a lot of it is, do you have a sense of how to attack a problem? All right, so my contact information is here. It's been a while since I think like this. All right, so I've talked a little bit about objectives. Obviously, I want you to learn how to do problem solving. Right, this is the main goal, but this covers a lot of different areas. So I want to emphasize more the techniques. How would you attack something? What are good skills to use? What are good things? What are good hammers to put in your tool bag? Strong advocate of programming. Out of curiosity, how many of you here are comfortable programming at a very basic level? For loops, stuff like that. All right, excellent. Everybody's hand is up for that. I'm happy to give some tutorials and stuff like this. I like Mathematica for two reasons. One, it has a really good interface. It has a lot of really good predefined functions. And two, I was a double major math and physics years ago and had to do a lot of Mathematica then. So that's become my go-to because first mover, that's what you use a lot. You keep using it. I can program in other environments. Mathematica is very fun. MATLAB is great. R is great for many different things. Don't really care so much what you're doing, but you want to be able to gather data. You want to be able to analyze it. This is a tremendously valuable skill to try to get a sense and a feel for the problem. So I want to make sure everybody is able to do that. We will do Project Euler problems. If you haven't heard of these are problems that are often trivial in principle, but extremely difficult to do before the universe dies at heat death multiple times over. Right? I give you a problem that's very straightforward. I give you a finite number of possibilities. Which one gives you the largest value for the function? Well, just try them all. But it may take so long to try them all that it's not practical. And there's a lot of things like that in mathematics where we have these wonderful problems where we know theoretically that there is an answer and we even know how to get there, but the amount of computational time it will take is disastrous. You can't afford to wait sometimes 15 years to get an answer for problems. So how do you attack these things efficiently? The other thing is, for some problems, rather than solving them, how do you just get close to a solution? For a lot of things, it's good enough to just be close, especially if we don't even know the values of the parameters we're putting into the problems exactly. So I want to show you good mathematics. So I was trained as a number theorist, so a lot of my examples will come from number theory, but happy to modify that based on what you're interested in. A lot of the problems we'll see are related to interesting mathematics and opportunities for research. So I know some of you are not graduating. So if you're not graduating and you're thinking of being an academic, you want to consider how should you spend your summers. And a good opportunity is to try your hand at research. So we have one of the largest programs of undergraduate summer research in the nation, which in an interesting twist is called SMALL. It's because SMALL are the first letters of the last names of the 5 professors who ran it in the first summer. And so I'll talk more about SMALL as the summer progresses, but this is a great opportunity to spend the summer with about a third of the people in the program are from Williams, the rest are from all over the country and the world, and just try your hand at research. Research is very different than most classes. Most classes, if section 3.2 is on the chain rule, what do you think you're going to use to solve homework problems that night? It's really hard to hide it in a lot of classes like that, right? In research, you don't necessarily know if the problem is even doable. And sometimes a lot of it is trying to figure out what is the right problem to look at. We used to have competitions. There will be at least one competition which we will be able to participate in. I sometimes scare people off because this class has the hardest final in all of Williams, and I will talk a little bit more about that in a moment. Oops. I think I have the grading. Yeah, I have the grading scheme here. So 50% of the grade is going to come from homework. 20% is going to come from class participation. You do not lose points if you say things that are wrong. You can only gain points by speaking up. Okay. Whenever you speak up in class, please try to shoot me an email later in the day about, hey, Professor Miller, these are the things I commented on. There's several reasons to do this. One, it helps me get to know you better. Two, whenever I have to write letters of recommendation, it gives me a list of items I can talk about. A lot of times the things are really trivial, but sometimes you may not realize that that was actually a really good comment that a lot of people don't know. It also helps reinforce the material by just writing and sending a note like that. Midterm is 10%, final is 5%. Does anybody know what the final is? The Putnam exam. So there's 12 questions, 6 hours. Each question is worth 10 points. What's the maximum score you can get? 120. If you get 1 point out of 120, that's a good score. Most people, I think more people get 0 than any other score on this exam. And you also have to remember, just to put this in perspective, most people don't take the exam. So if you get even 1 point, that's great. Right? So the curve is extremely generous. It's probably the most generous curve at Williams College. So you get 70% for showing up. And then every point you get, I add that to 70. So if you get 3 out of 12 questions right, that's 100. Okay? So it's at least generously curved. All right. Basically, this should tell you the final counts for essentially nothing. We do have a final for the class, but basically, as long as you show up, you'll be fine. It is good every now and then to take some exams with problems that are just truly challenging. These problems are doable. That doesn't mean that you'll be able to do them. But if you look at them just the right way, and that's one of the key things to get out of this course, is when do you get a sense of, can you look at this the right way? You have an advantage when you're taking an exam like the Putnam. There has to be a nice solution. I remember I was taking an analysis class with one of my favorite professors at Yale, Professor Jones. Wonderful, wonderful person. And this was either a real analysis or a complex analysis problem. And I had filled up several pages of calculations, and I was maybe a third of the way done. And then I wrote in the exam book, there's got to be a better way of doing this. And then I stopped, thought about it, and solved it in a paragraph. And he wrote in the margins, it's about time you realize that, Steve. It's an exam question. He's not going to give something that's going to require 8 or 9 pages of long calculations to be done in 50 minutes with multiple questions remaining. There's got to be a better way of looking at it. So on an exam that there should be a good way of looking at it. And if you're not, you might be able to do it. And there are some Putnam problems which you can brute force, and you might be able to brute force one of the problems if you spend your entire 3-hour block on that. That's not necessarily a bad strategy. If you think you can do one Putnam problem with 3 hours of long calculations and get every case, that might be a good idea. But there should be another way of looking at it. Life is not always like that. But you have an advantage when you're taking competitions. And we'll talk a little bit about strategies for how to take competitions. It's not true in life, but it's true in situations like this. How many of you are considering graduate school in mathematics? There is something called the Graduate Record Exam, the GRE. I will talk more about that when we have a recording malfunction. All right. Has everybody here done linear algebra? Okay, excellent. So as long as you've seen linear algebra, you've seen some proofs, you've seen more than enough. Out of curiosity, has everybody here seen proofs by induction? Everybody's seen proofs by induction. Okay, good. So again, this just gives you a little bit of a sense of how I want to adjust things. So my office hours are basically whenever I'm in my office, it is office hours. I will talk a little bit more about some issues that I have, but if I'm around, please come and see me. I'm always up for grabbing a meal, grabbing a coffee, going for a walk on campus. I'm a New Englander, so if it's minus 20 degrees and it's snowing, that's still walking weather to me. I know it's not walking weather for most people, but again, your goal should be to get to know at least one professor well every semester. I'm happy if it's me, I'm happy if it's not me. I am not going to try to get to know you. I don't look at the names of who's in my classes or anything like that. a little bit different than most Williams professors. Because when you leave Williams, you're not going to go to environments where the people are going to try to get to know you. You want to make sure I get to know you. You want to reach out to me. You want to get comfortable. It's hard. When I was an undergraduate, it was hard for me to reach out to professors. And it took me a while before I was comfortable doing that. That's a skill I want you to get. So please, I'm happy to do it individually. I'm happy to do it in small groups. I'm happy to grab a breakfast, a lunch, go for a walk, grab a coffee, just chat in the office, whatever. But I want to make myself available. So if you want to get to know me, happy to do that. Especially in a class like this, there's now the advantage of pitching it to what you're interested in. And again, this is a skill that will serve you well. You can also email me, and if it's between 9 p.m. and 6 a.m., I should be able to respond within 3 hours. So I'm usually very good at responding to emails. People who have taken classes with me before can confirm that. All right. Just a couple of links. And again, all of the slides are always going to be posted. So you can choose what you want to take notes on. But if I'm writing it here, it's being saved and it will be posted. Lots of handouts that I've posted. There's lots of opportunities, and I'll talk more about some of the opportunities to help later. I am the problem editor of the Pi Mu Epsilon Journal. I'm also affiliated with some other journals that have problem sections. And so if you're interested in trying to create some problems, happy to talk to you and work with you on stuff like that. And that gives you some math outreach, which is always a nice thing to do. Really good piece of advice is being prepared. This class is actually somewhat nice in that, for the most part, you're really not going to have much preparation to do for class. There's other classes where you have to be well prepared beforehand. You have to have read the material and be ready to discuss. A lot of this is thinking on the spot, which is both good and bad. There will be classes when we are absolutely stuck and don't know how to do something. Happens. And I wish I could solve all the problems. I can't. If you are one of the top 5 people in the nation on the Putnam, you're called a Putnam Fellow. I have friends who have been Putnam Fellows 4 times. One of my friends was only a Putnam Fellow 3 times because it only took him 3 years to graduate, which might even be more impressive than doing it 4 times. There are some people who can just look at these problems and they just know how to do it. I'm not one of those. So I expect to be stuck as well. I try not to prepare things in advance, which is both good and bad for me as well. So some things, I've taught some of these problems before, so I do know how to do some of them. But I will try to put things on that I don't know. And we'll do one of those. We'll do one that I know in a few minutes, but I'll pretend that I don't know it. Just so you get a sense of what is the thought process like? How do you attack something? That's what's going to be really important. So I want to mention a little bit about being prepared. One of the big things in life is you don't know which little events are going to create opportunities that will have a huge impact in your career. One of the reasons you come to Williams is for the network. This institution has, I believe, the oldest alumni society in the world. People love this place. They're always on the lookout for people from Williams to try to connect, provide other opportunities. You don't even have to go to Williams. As long as you know people from Williams, that's often enough to become part of the network. A couple of years ago, it turns out when you're an academic, what you really want for your birthday is a conference. And so we were having a conference for one of my thesis advisors, and my thesis advisor, I had 2 of them, Peter Sarnak at Princeton and Henrik Evanius at Rutgers. Peter Sarnak is so great, he's actually looped the mathematics community. I was the second Steve Miller PhD student. We were both born same year, same city. There's a lot of, we both moved away before we were very young, so we never met each other until grad school. He's smarter than I am, so he was actually finishing up my first year in grad school. He was on the organizing committee. We don't want to have 2 Steve Millers on the organizing committee. There were plenty of, I was not an organizer, but I was helping out with a bunch of things for the conference. And they had this at the Institute for Advanced Study in Princeton, very prestigious place. A lot of the top mathematicians in the world were there. And not surprisingly, several people were asked, do you want to make a speech, to Peter at the dinner? And I was not asked to say any words, and I was perfectly happy not to be saying words with, everybody present. I was not insulted. He has so many students. There were so many people there. But I prepared a speech anyway, just in case. And after the people gave their speeches, they then went and asked a couple of people randomly or semi-randomly, would you like to say a few words? And they handed me the microphone. And so I was very glad that I had prepared something just in case. And so there's a lot of times in life where you can do a little bit of prep work, and most of the time it may not matter. But every now and then you might be in a situation where you can take advantage of something. If you're going to a conference and you might run into some people who can impact your careers, read up about them. Be prepared. So as much as possible, try to think, what can you do to maximize your ability to take advantage of opportunities? Do we have any seniors here who are applying for jobs in the real world? Okay, applying to a job in the real world is essentially a full-time class. And so it doesn't have to be that, but if you have anything going on that is going to impact your ability to do anything for this class, as long as you give me at least a day's notice, I'm fine with moving deadlines. If you're applying to graduate school, if you have a big interview, if you have a big event where you're representing Williams, that's far more important than a homework assignment. And as long as you give me at least a day's notice, I have no issues moving deadlines. If you give me less than a day's notice, it's got to be someone is dying, you've been called to Washington, D.C. to fix the budget, something of tremendous impact where you could not know in advance. And even in those situations, I'm still a little bit skeptical and hesitant to give extensions, but I probably will. Because you want to prepare because you don't know when things will happen. One of my friends years ago, unfortunately, tried to kill himself before the end of his semester. And he's fine now, but that was not something I was expecting. And so fortunately, I had read ahead in my classes, and I was able to just essentially withdraw for a couple of days. You don't know when things will happen. You don't know when an opportunity will present itself or when one of your friends will need you. If you can get things done in advance, if you can get things done ahead of time, do so. If you're applying for like a National Science Foundation graduate fellowship, it's possible the website could go down. It's possible that the network could go down here. You don't wait till the last minute to apply for things. If you need letters of recommendations from professors, you want to give them preferably at least a month's notice and give them a lot of information to make things easy. All right. So your job is to be prepared for class. So if I give you some reading, do the reading. If I ask you to think about something, think about something. Come to me, come to each other if you have any questions. If there are things you want to see more about, if there are things you don't understand. My job is to provide resources. I have plenty of resources. I've been doing this longer than you've been alive. I have a very large network of people who write good stuff or know things. Happy to share all of that. And again, unlike life, you're at a small liberal arts college. We are not here because we want to be isolated and doing our research. We're here because we want to interact with students. So again, take advantage when you have the opportunities like this. So my brother gives 3 pieces of advice, and one of them is very similar to what I was just saying. So party less than the person next to you. For those of you who are at the edges, that kind of limits who you have to compare yourself to. But those in the middle, you actually have a couple of people to look at. Take advantage of office hours and mentoring. In the real world, you may be lucky and you may have somebody who really cares about mentoring. You may not. At a school like Williams, the professors really want to talk to you in all the classes. There's nobody who comes to Williams who doesn't want to interact with students. It can be very difficult and intimidating. When I was a student, I could not talk. I was an introvert until grad school. When one of my friends came up to me and said, "You should be a social chair." I said, "Don't you think a social chair should be somebody who likes being with people?" He goes, come. And so that night at dinner, I asked my friends, there's 3 social chair positions. If somebody will do it with me, I'll put my hat in the ring. And one of my friends said, "I'll do it." And it was one of the best things that happened to me. And again, it's those taking advantage of opportunities when they arrive. It really did more for me than almost anything else in graduate school. Got me to the point where I was comfortable talking to people. It's not easy, but it can be done. The last one is learn to manage your time. It is amazing how many people do not manage their time and they wait, and then everything gets put off to almost the last minute, and you may not have the ability to do something because you've got to get this finished. Whereas if you got things done earlier, you could then take advantage. I will try to have the homeworks due after we cover the material, so you have plenty of time to get it done and just be working on the other things. Things will happen, especially in some of your other classes. If you can, read ahead. Build up a strategic reserve in your classes. Especially, maybe hard to do that now, but during winter study, build up a strategic reserve for the spring. Read ahead so that as the semester progresses, you've got that little bit in the bank. For those of you, it doesn't seem like anybody's applying for things in the real world. I'm happy to do practice interviews. As I said, I'm happy to adjust deadlines and all that stuff. Just all this stuff will be on the web, but just, has everybody here used LaTeX? So everybody has used LaTeX before? Okay, so it's really good to learn how to write math well. One of the greatest dangers of LaTeX is now it makes almost anything look like good math. So you have a lot of people who post things and it looks good. And when you're searching the web, you always have to be careful. Can you trust it? I probably, there's a few things you regret in life. I was in South County a few years ago, and there was a beautiful quote. It was a picture of Abraham Lincoln, and it was, the problem with the internet is you can't trust everything on it. And so you've got to be careful. Can you trust something that's posted? Well, in mathematics, you can actually go through line by line by line and check and see, is this valid? And I remember years ago, I needed a proof of a standard result, and I did a quick search, and I found something online. And I looked through it. Yep, looks good. The person had also posted a 2-page proof of Fermat's last name. What he had posted for the other one was correct. It was the standard proof. But all of a sudden, oh, he's... Be very careful what you see out there. Just because it looks nice now, 20, 30 years ago, if something looks nice, almost surely that's being done by a professional. Nowadays, it's something you need to learn how to do, but just be careful as you're looking. I've got a bunch of templates for giving talks, for writing papers. Happy to share all of those. All right. Any general questions now before we start doing some real problems? Any questions or concerns about the course? I will share just one of my favorite stories. It was my first year teaching. I was teaching differential equations in the spring. And at the time, and I think it's still true, Williams does not require linear algebra as a prerequisite for differential equations. I'm happy to have arguments as to, is this a good idea or a bad idea? You can't not do systems of equations, like predator-prey, population, stuff like that, when you're doing differential equations. So I wanted to just do some basic 2x2 matrices. But linear algebra was not a prerequisite, but everybody must have seen 2x2 matrices. So I asked the class, is everybody comfortable with 2x2 matrices? Silence. Does anybody want to see a review of 2x2 matrices? Okay, so everybody's fine with 2x2 matrices. Okay, now this was back before everybody had cell phones. That's how old I am. We had what's called clickers, where you'd pass out these devices and they would have the numbers. I said, I'm just curious. I'm not going to report the results to the class, but I'm curious. Press 1 if you want a review of 2x2 matrices. Press 2 if you don't. I never said I wouldn't present the results to other people. I just said I wouldn't present the results to the class. You've got to be very careful in what you say so you don't lie. 43 or 47% of the class wanted a review of 2x2 matrices. 0% raised their hand. Now, I was younger and I looked more intimidating, I think, back then than I do now, but 43%. So almost surely, not just in my class, but in any class you're taking at Williams, if there's something you want more detail on, if you ask a question, you might see somebody rolling their eyes or sighing. Oh my God, I can't believe they're asking this question. Whereas other people with better poker faces were like, yes, they asked the question. Thank God somebody asked the question. So again, I'm strongly urging you, if there's something that you want more detail on, if there's something that's not clear, almost surely you're not alone. Hopefully this is a small enough class that people will later say to you, thank you for asking that. But if not, at least 1 or 2 other people will be thinking that in their mind. All right. This is one of my favorite problems. I have posted this on my Math Riddles page. This is often one of the top sites when you do Math Riddles searches. I started this when I was in grad school. I haven't really done too much in terms of maintaining it, but if anybody's interested in math outreach, there's a lot we can do with something like this. I get emails every day from teachers all over the world who try to use problems like this to excite their students. And there's often a lot of good mathematics behind this. So for this one, is this large enough that people can read it? Okay. I can also do this. So it's weird. For me, I need my glasses now if I'm reading something that's close. If I stay far enough away from things, I can see it. So you take the numbers 1, 2, 3, all the way up to 9, and you use each number once and only once, and you want to form 3 fractions. And the numerators are always 1 digit, the denominators are always 2 digit. And if you do it properly, you can get the 3 fractions to add up to 1. So 1/23 plus 4/56 plus 7/89. This is not doing it properly. This is just a straightforward, very simple way of doing it. You know, that does not add up to 1. There is a way to do this. Okay? If you've seen this problem before, or if you've ever seen any of the problems that I'm doing, you've become mute. Okay? So if you already have seen it, you cannot speak up. Okay, don't spoil the fun for others. Does anybody have any thoughts about how you would attack a problem like this? And yes, this is a 300 level class and we're talking about adding fractions. So we have 1, 2, 9, and a over 10b plus c plus ... No, 2 plus d over 10e plus f plus g over 10h plus I equals 1. How can we find out how to do that? Each number is used once and only once. I don't care if it's a good method. Can you give me a method? Try everything. For cultural extra credit, what movie has the song Try Everything? Disney movie.
Is it Zootopia?
It is Zootopia, so you can email me for cultural extra credit. It's a good song. So try everything. How many everythings are there? Not 9. You're close. It's not 9. It's close to 9. Not 10. It's 9 factorial, right? There's 9 factorial ways to do things. What I love about this is I was at the American Institute of Mathematics. I was surrounded by some of the top number theorists in the world, and they started proving some lemmas about where some of the digits have to be. And I noticed 9 factorial isn't that big. What's the largest factorial somebody knows off the top of their head?
720.
Okay, and what's 720? Is that 6 factorial?
Yes.
So 6 factorial is 720. So 9 factorial is 9 times 8 times 7 times 720. How big is 9 times 8 times 7?
Like 500.
So is it more or less than 500?
More.
Probably a little bit more than 500, right? It's definitely less than 1,000. So you might say, look, this is maybe roughly around 500, roughly maybe around 1,000 over 2 times 720. So maybe this is around 360,000. So maybe 9 factorial ballpark is around 360,000. It's a little bit less than that. The ballpark that gives us a sense. It's not that bad for a computer to check 360,000 items. What I noticed is without loss of generality, when you look at the 9 digits, where can you assume the 9 lives? No, you cannot assume the 9 lives in the numerator. Why do you think the 9 has to live in the numerator? It turns out you are right. So you might be able to give me a good explanation right now, but why does the 9 have to live in the numerator?
I guess by thinking it's like get close to 1, you probably need some large number over like a small.
Good, so you probably need a large number over a small number, but maybe the 9 doesn't have to be the numerator, maybe it's the 8. But where, without loss of generality, it's one of my favorite phrases, without loss of generality, the 9 lives where?
Probably not the first digit.
But again, you're gonna have to then use, it's probably not, well, but maybe Maybe it's one of the fractions is a very small one. But without loss of generality, we have 3 fractions. Where can you say the 9 lives without loss of generality? Which one?
One of the 3.
Which one? Without loss of generality, the first, right? Without loss of generality, we can assume, and we can split into 3 cases, lives in first fraction, split into 3 cases. So if we do that, we're going to have, case 1, 9 over 10a plus b. Case 2, let's say a over 10 times 9 plus b. Is this clear enough notation what's going on? A over 10b plus 9. How many possibilities here from this point onward to fill everything in? So we have 8 factorial, 8 factorial, 8 factorial. So it is 3 times 8 factorial versus 9 factorial. So that's a factor of 3 savings. Is a factor of 3 savings good? You have an interesting expression on your face. Is it good?
I guess it's better.
It's better. So one of the things that you have to think about is how much is something worth to you? How many times are we going to use this? We're going to write a computer program to solve this. How many times are we going to run the computer program? Well, no, I'm saying we're going to write the whole program. How many times do we execute the entire program? Once. My brother works at MATLAB. I'm sorry, MathWorks, the company that makes MATLAB. They make a lot of things that go tremendous applications and phones and various things. If you're doing something billions and billions of times, you want to be efficient because a small savings adds up. I'm running this program once. What I noticed back when I was a postdoc as I was doing this problem is I could code that 9 is in the first fraction and split it into 3 cases. 9 factorial is such a small number, it would actually take me longer to code the program efficiently than to just write the program. Not worth the savings as run only once. And this is a really surprising observation, that it doesn't help us to be clever because we're going to spend so much time coding that split that the program runs so rapidly, it's just not worth it. So as an exercise for Monday's class, see if you can write some code to find how should you put the numbers. Let's try to just get a little bit of a sense of what can we say about where some of the numbers must be. Can we do some things to help us? So we know that without loss of generality, the 9 has to be if we want in the first fraction. But several people were trying to say maybe the 9 has to be in the numerator. If we had a result like that, that would greatly simplify things. If we knew the 9 had to be in the numerator, great. Now all of a sudden we've now fixed it and now we truly have only 8 things to loop over. What else, instead of the 9 being in the numerator, is there any other number you might have a sense of where it has to be? So hopefully this will work. Okay, it did work today. So let's go back to this expression. The hope is that maybe 9 has to be in the numerator. Can you give me any other numbers where you might have some idea where they might be? Yeah, where do you think 1 is in the denominator? Yeah, B or E or H is 1 is maybe one of the tens digits in the denominator. Why?
makes the fractions as big as they can be.
It makes them as big as they can be. And so if the fractions are too small, they're not going to add up to 1. So, oops. So let's say, imagine the largest tens digit is a 3. Could this work? So that means, B, E, and H are not 1 or 2. So the largest tens digit is a 3. Is it possible that the fractions could add up to 1? What do you think? Yes?
Yes. I guess like if you do like
So the tens digits can't be a 1 or a 2. Let's say we're trying to see if this is a result. So 3 is the largest of B, E, and H. What could you say about the size of each of these fractions if the largest of B, E, and H is 3?
those less than a third.
It's at most less than a third, so they're less than a third. So in this case, each fraction is less than 10 over 30, which is 1/3. Cannot add up to 1. So we've just proven that at least one of the fractions has to start with a 1 or a 2. And again, yes?
Sorry, could you imagine the smallest tens digit is 3?
Oh, sorry. You're right. Sorry, you're right. Yes, I meant smallest and largest. I apologize. Yes, the smallest. Thank you. So imagine the smallest of the tens digit is 3. So we don't have a 1, we don't have a 2. Then in that case, each fraction is less than a third, and there's no way that can work. So we've just shown that one of the fractions has to start either with the 1 or a 2. Building on this, what should we attack next? Two. So imagine the smallest tens digit is a 2. Could that work? So let's try to imagine what could happen. Let's try to think about what's the largest we could have. Okay, 9 over 21. I like your thinking. So we'll put in a 9 and a 1 here. What next?
8 over 34.
8. So we could do 8 over 34. Do you want to do 8 over 34?
Same for that last fraction.
Yeah, I probably want to say 4 for the last fraction. So 8 over what? Probably 35, and 7 over 46. This is playing a little bit fast and loose with the mathematics, but my feeling is that this is probably the largest I can do if the smallest tens digit is a 2. I definitely want to put the 1 and the 9 in that first fraction, those spots, because that's going to make this part as big as possible. If I put an 8 over there, percentage-wise, I'm losing so much from that as opposed to the other places. Can anybody do that fraction in their head?
I just approximated them as decimals. I think it's like about 0.85 or 0.86.
Okay, so you're using the approximations. I actually calculated this at home. I did actually prepare a little bit. for today's lecture. And so when you add them all up, if I have done this correctly, you get 1303 over 1610, which is less than 1. So cannot have 2 as the smallest 10. Yes.
So I guess like the next approach would be to just like start with 1 and then just try to make the highest possible sum.
So now we know that we have to start with a 1. So we know it has to be plus, and we know there has to be a 1 over here. And so this is known. And so now we have 8 factorial possibilities. Anybody want to guess what the numerator is? Why not? So you can try it. And then there would only be 7 factorial possibilities if that's correct. Do we know that that's correct? No, we don't know that the 9 has to be there. But we do know as a theorem that one of the fractions has to start with a 1. Without loss of generality, we might as well make it the first fraction. If you want to try the 9 over the 1, anybody have any other guesses that they might want to try for the next one?
I think we should put 2 as like the starting, as the first digit of the next denominator.
So if you do that, I think it's going to get too large. Or
I mean, like we can just try it. So far, all of our numbers have been too small, so we should just try finding max.
so one possibility is we could try putting a 2 over here as the 10. Any other thoughts where you might want to try to put the 2?
It's the first, the other digit for the.
So you could also try putting the 2 over there, maybe. At this point, it's not clear which way is best. If you try the 9 over 12, then you only have 6 factorial things to try. And of course, you actually have a little bit of a savings because you can flip the 2 orders of the fractions. And so for a lot of these problems, you're welcome to try some things and just hope it works. At this point, it's starting to get very involved in terms of trying to come up with something more meaningful to say. So again, I don't think you're ever going to be in a situation where you're asked to take numbers like this and add them up and get 1. What I like about this problem is the thought process. And the best thought process is, let me write some code to investigate. And this is not a bad program to write. And so the question is just, what's the easiest way to deal with things? Since we only have to run the code once, we don't have to be that efficient. It is possible to do some things to make your life a little bit easier. Without loss of generality, we know the 9 has to be in the first fraction, but we don't know if it's numerator or denominator, and if denominator, we don't know where. We can, however, prove that one of the fractions has to have 1 as the 10th digit. And that does lead to some savings. So anyways, this is what I really want to do in a class on problem solving. I want to talk about the thought process of how do you attack stuff like this? How do you leverage the different skills and the tools we have available from your ability to think, as well as the ability for computers to do tedious calculations for you? No one wants to check 330,000 cases, but the computer will do that for us. All right, so I think this is a good place to stop for today. I will stick around a bit in case anybody has any questions.